Hi guys, I hope you've had an amazing Easter and are ready and raring to go with continuing the work that we've been doing on waves. So after we left school, but before we broke up, I got you doing a little bit of work on sound, and we will come back to sound later on in the course, but I want to come back and finish off the work that we've been doing on light. Now, before we broke up, we kind of looked a lot about refraction. And I think for most of you, I did show you dispersion occurring. So that is when a prism can be used to break white light up into a rainbow effectively. Although I showed it to you at the end of a lesson, because we had the ray boxes out, we never actually sat down and went through how it works. So that's what today's lesson is going to be on. It's going to be on dispersion. So in order for us to understand dispersion, we need to go back and just quickly recap refraction. Now, with refraction, we need to understand that when a wave moves from one medium to another, it can speed up or slow down. We've seen this with both water waves going from shallower regions to deeper regions, and therefore speeding up, or vice versa. Obviously, going from a deeper region to a shallower region, it's going to slow down. But we've also seen it with light. So as light goes from something like air into glass, into a denser medium, it's going to slow down. Now, if the whole wave enters that region at the same time, then nothing's going to happen other than the wavelength changing. So as it slows down, the wavelength is going to decrease. But if it happens at an angle, that's going to cause refraction to occur. Now, why does this happen? Well, if we look at this wave approaching this barrier, when we get to this point here, this section down here has entered the denser region, or the shallow region first, and has therefore slowed down. If we then move on again, this one now here has again slowed down, and has therefore fallen behind the rest of the wave. If we keep progressing this, we'll see that that wave has actually changed direction. So here is the original direction of the wave, and this is the new direction of the wave. So because as it entered that denser region, or that shallower region, the wave slowed down, we've seen not only a decrease in the wavelength of the wave, we've also seen a change in the direction. And it's that change in direction at the boundary between the two media that we call refraction. Now, don't worry about putting this into your notes. This is already in your notes from previous work that we've done. So if you want to go back and read through them, just to familiarize yourself with these terms again. But this is the kind of the core of what causes refraction to happen. If you think about the lesson, you know, I always make a bit of a fool of myself by walking along with my arms held out. And you can try it yourself out. Try it out yourself. Now, stand up right now. Walk along with your arms held out either side of you, and try and slow down one of your hands without slowing down the other, and see what happens. The only thing that happens is you are going to turn, and that turning is what we call refraction. So when we first looked at the refraction of light, we did it in terms of a rectangular glass block like the one shown. So we would have taken our rectangular glass block and placed it onto a piece of paper, and then we'd have used a ray box to shine a ray of light into that glass block as shown. Now what I want you to do is I want you to think about yourself walking along that line with your arms outstretched in front of you, or either side of you, sorry. Now as you're doing that, your left arm is going to enter that glass block before your right arm, and therefore you are going to turn slightly to the left. As I've shown here. Now, really, in order to be able to quantify this or really discuss it, we need to add in what we call the normal. Now, the normal is a line perpendicular or at right angles to the boundary between the two media. So that's this line here. That enables us to actually add in two angles. So that is the angle of incidence here and the angle of refraction here. So we can see that as light enters a denser medium, it bends towards the normal. So our angle of refraction is very clearly smaller than our angle of incidence. We bent towards the normal. Now I want to look at this interface up here, because the light now has to leave that glass block. Well, again, imagine yourself walking along this line here, with your arms out. with your arms outstretched to either side of you, and your left arm again is going to leave that glass block and is therefore going to speed up before your right arm, and therefore you're going to turn to the right. Again, I'm going to add in a normal, and that enables us then to look at the angle of incidence and the angle of refraction. Now you can see here that this is the angle of incidence because it's the one that's striking that boundary. This is the angle of refraction because it's the one that has been refracted at that boundary. So in this case, that ray of light has actually bent away from the normal rather than towards it. So when light enters a denser medium, so it goes from air to glass, for example, it bends towards the normal. And when it leaves a denser medium, so it enters a less dense medium, it bends away from the normal. Now, the other thing to note here that we would have put onto this when we did it originally was to say that the amount that the ray of light bends towards the normal is equal to the amount it bends away from the normal on entering and leaving the glass block. And that means that the incident ray, this ray down here, and the emerging ray are in fact parallel. So the incident ray and the emerging ray are parallel. Again, no need for you to put this into your notes because we've already done this. This is just a recap. So in order for us to understand what's happening with dispersion, we also need to know a little bit about light. Now, we've already discussed what light is. Light is a wave. It's actually an electromagnetic wave. Now, I don't really need you to understand what an electromagnetic wave is. All I need you to understand is that light is a wave. And I also need you to understand what is different about all of the different colours. And what is different is their frequencies and wavelengths. They are terms that you should be familiar with. If you're not, go back over your notes, have a look at what we mean. Frequency is the number of oscillations per second. Wavelength is the distance between two successive peaks. So if we look at this diagram on the left-hand side, we can see that at this end, our blue end of the spectrum, the light has a wavelength of in the region of 400 nanometers. That's 400 times 10 to the minus 9. So I'm going to take 400 and divide it by 10 9 times. And up here, we've got red light, and that's got a wavelength in the region of around 800 nanometers. So all the other colors sit in between those two extremes. Now, one of the things that you might be asking is, well, where is white? Well, white is not a color. White is in fact actually a combination of all the other colors. If we mix together all of those different frequencies across that full spectrum, we are going to get white light. So when we get white light from light sources like light bulbs, that isn't its own color, it is all the different colors being emitted from that source. Okay, so that is very, very important for us in order of our understanding of dispersion. So just to recap, light is a wave, it's an electromagnetic wave. The frequency and wavelength of that electromagnetic wave is going to determine the color. And white light is a mixture of all of those different colors. So here I've got a prism, and I did show you this right at the end of our last lesson together. Although we didn't actually put anything into our notes, because we had the ray boxes out, I got the prisms out and we just had a quick look at it. But this is a prism, and what we're going to do is we're going to shine a ray of white light into that prism. Now, if you think about what we've just discussed in terms of refraction, think of yourself walking along that line. In this case, it's your right arm that is going to enter the denser medium before the left arm, and therefore you're going to turn to the right. So we're going to come out there. The light bends towards the normal. Now, when we leave, again, if I put the normal in again, this time we're going to bend away from the normal. So actually, what we're going to end up with is a very large angle of deviation. So with the rectangular glass block, we ended up with our angle of incidence and our emerging ray being parallel, whereas here we've actually ended up with a very large angle of deviation. So if you want to put this diagram into your notes under a title of prisms, that's going to be also under a title of dispersion with a side heading of prisms. That's going to be really useful for me. So remember, don't make it too small. Nice large diagram in your book, taking up at least a third of a page. I want it to be absolutely identical to this. Draw it with a pencil and ruler, label in exactly the same way, and then have this statement either below it or to the side of it. So when light passes through a triangular prism, the refraction on entering and leaving causes the emerging ray to be deviated from its original direction. So how does this cause the light to be split into its constituent colours? Well, each of the different colours has a different wavelength and is therefore refracted by a different amount on entering and leaving. So the red light is deviated the least, and the violet light, or the blue light at the end, is going to be deviated the most. So let's just look at what happens therefore at this initial boundary on entering. Here we can see they both turn to the right, they've both bent away towards the normal, but the red light hasn't deviated as much. It's only refracted a small amount, whilst the blue has refracted a large amount. When they then both leave, that actually is exaggerated. So again, on that boundary on exiting here, we can see that the red has deviated a small amount, the blue has deviated a large amount. Now what that's caused is that blue and that red light to actually come out at different locations. And don't forget, this is just the extremes. We've also got all the other colours in between. So we've got all of our colours, red, orange, yellow, green, blue, indigo, violet, spread out into their constituent colours. Now that order is quite important. I really want you to remember that. I use a nice mnemonic to remember it myself. That's Richard of York gave battle in vain. But you can use any mnemonic if you would just rather just learn that list. But please do remember the order in which those colours come out of a prism. So it's this splitting of light into its constituent colours that we call dispersion. So again, this diagram shows what I've just had on the diagram before, but just a little bit more colourful. We've got the white light coming in here. So this is in our emerging ray. At this first boundary, we're going to have the light splitting into its constituent colours a small amount, and that is then exaggerated at this second boundary when it leaves the glass block. And if we place the screen here, I think we used a piece of paper when we did this in class, you're going to see all of those constituent colours very clearly separated from each other. I'm going to show you a video now of somebody showing this in real life.
Light dispersion and refraction through a prism. Have you ever noticed that diamonds sparkle in sunlight? Ever wondered why? They sparkle and seem to be giving out different colors. Just like oil spilt on any surface showcases different colors. The reason behind this phenomenon is the refraction of light. Before we understand what refraction is, let us conduct this easy and cool experiment of extracting a rainbow from white light. For this experiment, you'll need a prism, white light, and a dark room where the refraction can clearly be seen. Procedure. Take the prism and keep it on the table. Ensure that the room is considerably dark for the light to be obvious. When light travels through the prism, it splits the white light into 7 colors. These are violet, indigo, blue, green, yellow, orange, and red. They appear in the same order, just like in the rainbow. Observe the light ray carefully inside the prism. Notice that the light ray bends at 2 different points. One when the light is entering the prism, and another when it leaves the prism. The question is, why is the light being dispersed into the rainbow colors? Explanation. Prisms are made up of glass. The 7 different colors coming out of the prism constitute 7 different wavelengths. Each color represents a different wavelength of light. These different wavelengths travel at different speeds in the glass. This is the main reason for the formation of a rainbow or spectrum when the light travels through the prism. Another point to be noted here is that the angle of refraction is different for these colors as they have different wavelengths. When light touches the surface of the prism, refraction takes place at the boundary of the prism. In example, boundary between air and glass. Then the white light is separated into its component colors: red, orange, yellow, green, blue, indigo, violet. Refraction is the change in direction of a wave due to a change in its medium. When these wavelengths reach the other side of the prism at different angles, refraction takes place at the surface of the prism, i.e. at the boundary of the glass and the prism, and the angle of refraction is greater when they leave the prism. This separation of visible light into its different colors is known as dispersion. All these colors constitute the spectrum.
So we've just seen there a nice video of dispersion occurring in real life. And I also want to just give you another example of where we see it, and that is with rainbows. So a rainbow is a really nice example of dispersion occurring. It occurs because as the white light from the sun travels through the atmosphere, if it's raining, that light is going to pass through water droplets. And those water droplets have got a higher density than the air around them, and so the light is going to slow down when it enters them. And if it happens at an angle, we're going to get refraction occurring. And that, because of all those different colours refracting by a different amount, it's actually going to split that white light into its constituent colours. So that's all rainbows are. It's physics.